Hello, welcome back. This is Dr. Mike Kabuki, and I'm continuing my series of lectures on acid bases. This is the third video, and we will be looking at bases to begin with in this video. So, strong bases. What are bases? What we say bases are proton acceptor from the Bronsted-Lowry definition, and also from Arrhenius' definition are the OH. OH source. Okay, OH or proton acceptor. Okay, some examples of bases are the group 1 element hydroxides. That's sodium hydroxide, lithium hydroxide, and also the alkali earth metal hydroxides. These are group 2A, magnesium hydroxide, calcium hydroxide. Those are the list of strong bases. What do we mean by strong? That means they can dissociate completely in water. Okay. Now, calcium hydroxide, one important property of this compound is that it has low solubility. It has some uses. You will see that it is used for removing gases, removing stacked gases to remove sulfur dioxide from the either towers or chimneys. These are very useful in the process of lowering the acidity of gases that are produced into the atmosphere. And another important use is this of calcium oxide and sodium carbonate. These are used for water softening process. Now let's look at calculation of pH for strong base. Strong base is sodium hydroxide, and given the concentration, we can expect the same steps in the calculating the pH in strong acids. Look at the dominant species. The dominant species will be Na plus and OH and water. So the contribution that will govern the pH will be pretty much the concentration of OH. So if you look at the concentration of OH, that will be the same as the concentration of the sodium hydroxide to begin with. Why? Because of the strong base. So you can put in the calculation. After getting the concentration of hydroxide, you can find the concentration of hydrogen ions by substituting into the Kw expression. So Kw is 10 to the minus 14, and this one is 5.0 times 10 to the power of minus 2, and then work out the hydrogen concentration. That will give you 2 times 10 to the power of minus 13. So that's the concentration, and that will give us the pH. We use the relationship for pH. Note that this is a basic solution. A basic solution has a pH above 7, and 12.7 is that that example. Okay. Now in the bases, the concentration of OH contributed from water in that equilibrium is negligible. We're taking it that it's not so significant compared to the concentration of the strong base. Now when you look at the other types of bases, you're going to look at not only those that has hydroxide ion concentration, but you will be looking at those that has what we call the amine group in their structure, and those are what we regarded as lone pair electrons or proton acceptor. So you have at least one unshared electrons in the structure. Now in that case, you look at the equation for the ionization of a base in general. So this will be a base with water. It will be the conjugate acid, that is, or proton, that is accepted by the base to form the protonated BH plus, and then releasing that base species, the OH minus. So the equilibrium constant this time will be Kb instead of Ka. So it'll be the concentration of BH plus multiplied by the concentration of OH minus over the concentration of the base. Now, for weak bases, you'll find that Kb will be very small. So that's the same of what we have already seen for weak acid. Some examples of weak bases. For example, ammonia is a weak base. And the derivatives of ammonia, you'll find that methylamine, dimethylamine, trimethylamine, ethylamine, these are all ammonia-derived molecules. And we know that ammonia has this structure, NH3, which is 1N and 3 hydrogens. Okay, and then the lone pair. Now, if you remove one hydrogen, you can substitute that with one of the group that we have here. So, for example, CH3. And that's methylamine. And you can remove this hydrogen and substitute it with another methyl group, that will be dimethylamine. And you can remove this and substitute it with another methyl, that will be trimethylamine. So that's the nature of the structure of the amines. And you will see this nitrogen with a lone pair in all these structures. So that's the structure. Let's look at how to calculate the pH. So notice that this is a weak base. We already noticed that. So calculate the pH of 1 molar of methylamine. So this is a weak base. So how do we set up this problem? We are going to look at it in the same way as we did in the weak acid. Establish the main equilibrium, which is the ionization in water to form the conjugate acid. That's the conjugate acid. This is the base conjugate acid. This is now the acid conjugate base. So let's write the Kb expression as products divided by the reactant. Now we can set up the ICE table. So the initial concentration is 1 for methylamine. There is 0 and 0. We don't have to worry about water because water is not included in the equilibrium. So the change will be minus x plus x plus x. And so at equilibrium will be these quantities, 1 minus x, x, and x. So now we can substitute in the equilibrium. Let's substitute the equilibrium constant expression. So Kb is equal to 4.38 times 10 to the power of minus 4. And that is equal to x times x over 1 minus x. Now this is where we make that important approximation or assumption that this term here is essentially equal to 1. Approximately equal to 1. So x rather small, so you can make that approximation. It must be valid if it's less than 5%. So the approximation is tested, and you can verify that it is less than 5%, so it is good. Now you can work out the OH concentration. OH is equal to X, which is 2.1 times 10 to the power minus 2. We can work out the pH of that, POH, sorry, POH, because this is OH. And then find the pH by subtracting them from the 14 value, 14 minus 1.68. So this is the answer. And we should expect it to be a base because this is greater than 7. Okay. All right. So, in other words, when you're dealing with the calculation of weak bases, we follow basically the same step as we've done in the weak acid. But remember, when we are doing that calculation, we are using Kb. We are using Kb, and we are calculating the OH concentration. And remember that to find pH, you have to find the pH from subtracting that from the total pH, which is 14. Now let's look at polyprotic acids. Polyprotic, one that has more than one hydrogen that are exchangeable in their structure, and we have quite a number of acids that are polyprotic. So one common example is this one, phosphoric acid, H3PO4. Now when we dissolve phosphoric acid in water, you'll get 3 Ka values, Ka1, Ka2, Ka3. These are the Ka values, so that's phosphoric acid. Dissociate the first proton to give you H plus and H2PO4 minus. Second proton will give you HPO4 2 minus, and the third proton to give you just PO3 minus with H plus. So in other words, you expect 3 Ka values, A1, Ka1, Ka2, Ka3, and these are the relationship of the equilibrium. So when we're looking at this acid, this is something we'll find. Typically, Ka1 is greater than Ka2 is greater than Ka3. So in other words, this Ka1 will be greater than these other two. So there is a significance of this. We will look at that. We note that in most of the acid, the second and third proton occurs less readily than the first. So the loss of the second and the third proton occurs less readily. So in other words, that means we can just focus on the first equilibrium. That is the ionization of the first proton. And that will simplify our problem as we solve this. So for a typical polyprotic in water, only the first dissociation is the significant one. All right, let's try and look at this. So now let's look at this example. Calculate the pH of 5 molar H3PO4. So this is a polyprotic, and it has ionization constants 1, 2, and 3. So these are the species that are going to be present in solution other than the H plus, H3PO4, H2PO4, HPO4, and PO4 3 minus, of course, with their charges. So how are we going to approach this? The major species in solutions, again, we're starting with this sort of step, will be the starting acid and water. So that's the major species. None of the dissociation products of H3PO4 is written since the Ka values are so small. That's why they are a minor species. So the dominant equilibrium really is just the first one. H3PO4 losing a proton to form H2PO4 1 minus. And setting this up, you find that that's Ka1, 7.5 times 10 to the power minus 3 is the concentration of H plus, concentration of H2PO4 minus, and divide by the concentration of H3PO4. All right, so here is the next step. We can set up the ICE table, start with the initial, the change, and the equilibrium concentration. Notice that we are just dealing with the first ionization. We are not concerned about the second and the third. So let's substitute the values in the equilibrium constant. That is Ka is equal to x multiplied by x over 1.0 minus 5.0 minus x. And that is equal to this. Again, please note this step here, which is the approximation. We are using the approximation step, which, as I say, is a lifesaver in this sort of mathematical problem. So once you make that approximation, solve for x, you'll get 1.9 times 10 to the power of minus 1. Now, this is a step that you always have to carry out, validate it. In other words, check whether it is less than 5%. So you can do that calculation. I'm not going to follow that through. And it is in this case. And now, that is the value of H plus, 1.9 times 10 to the power minus 1. Then find the pH. So that's the value of the pH. So these are the concentration we have established. The 2x value, H plus and H2PO4 are or is 0.19 molar, okay, because they are the same. And now the concentration of H3PO4 from that equilibrium will be 5 minus x, which is 4.8. We can follow through and calculate the concentration of the other equilibrium species in the second and third equilibrium. So that's what we will do. We are going to use Ka2 and find the concentration of Ka2 will find the concentration of H2. Let me see. HPO4 2 minus. The concentration of HPO4 2 minus. And we can follow through. Let's just go back in here. Ka2 will be equal to HPO4 2 minus over H2PO4 minus. Yeah, that's missing in here, the H2PO4. So we know the concentration of this and this from the above. And we know K. Now we can work out the concentration of HPO4 2 minus. So we can apply the same for the third equilibrium, because now we know the concentration of HPO4 from the above and H plus. Notice that H plus is the same throughout all these steps. And now we can calculate the value of PO4 3 minus. And that is the concentration. So now you can see how easy we solve this problem by establishing only the dominant equilibrium and not worrying about the other two lesser significant equilibrium in this sort of problem. So that's what we do when we are dealing with polyprotic acid. So the result shows that the second and third dissociation steps do not make any important contribution to H. And this is apparent from the concentration we've calculated. You can see how low those values are. and that shows the validity of the assumption taken in this. Okay. Just for interest's sake, what if the three values of Ka for phosphoric acid were closer to each other in the value? That will be a complicated solution. In other words, we have to use the mathematical approach step by step, and it's not going to be very easy. So we may consider that in other contexts or in the upper division chemistry courses, but not for our level. Now let's look at one example or unique example of a polyprotic acid, and that is H2SO4, sulfuric acid. Now sulfuric acid is a strong acid, so in other words it dissociates completely. But notice that it has two dissociations. The first, losing a first proton, that's Ka1, and losing the second proton, Ka2. Notice this value. This is very large and it's not recorded. That means it's almost 100% there. And here is 1.2 times 10 to the power minus 2. Watch this number here. It is not regarded as so small. The reason that this is still not as small compared to the values we've been calculating from the previous example. We'll see next. Okay, let's go in here. Calculate the pH of 1.0 times 10 to the power minus 2 molar H2SO4. So, in here, what we can say is this. This is a strong acid. The first dissociation will go to completion, right? First dissociation. But the second dissociation, that's the one that we're going to deal with. Okay, let's look at the major species. Major species will be H+, HSO4, and H2O. You notice here that we are dealing with the second equilibrium species. So now let's consider that, the dissociation of the second equilibrium species. Draw the IC table, HSO4. Now assuming now that is a strong acid, H2SO4 dissociated completely, so 0.01 mole of H2SO4 is 0.01 of HSO4. All right, so let's come to the ICE table. One interesting observation in this, because we are dealing with the second dissociation, notice that the first dissociation of the acid itself already gave 0.01 molar of H+, right? Remember that, 0.01 molar of H+. So we cannot say that this is 0 anymore because of that. Yes, this one we can still have that 0 initial, but this one no, because we are dealing with a second equilibrium here. The first one was a complete dissociation, so it yielded this quantity of H+ and this quantity of HSO4 minus. All right, let's look at the change. It will be minus x plus x plus x, and at equilibrium 0.01 minus x. Now notice now 0.01 plus x, and this one is x. All right, so let's look at the equilibrium constant expression. You will get this concentration of H+ is this, concentration of SO4 minus is x, and concentration of HSO4 minus is x, 0.01 minus x. Okay, now can we use approximation? We can try. So if we make the usual approximation, that means this will be approximated to 0.01, and this will be approximated to 0.01, right? So what do we get? 0.01, 0.01, x. So you'll end up with x because these two will cancel out. So that's what we get, 1.2 times 10 to the power of minus 2, which is 0.012. Now, if you're following this calculation and the values carefully, this is a little bit strange. Why? If you start with 0.01, how can you get 0.012? Ridiculous, right? That's exactly right. So in other words, the usual approximation doesn't work. In other words, the assumption is not applied in this. So what do? We have to solve the polynomial. So in other words, in this case, it's going to be a quadratic equation, and we must follow the full solution. So you have to write this out in a quadratic form. Ax squared plus bx plus c equals 0, and that's the setup that we are trying to get here. That's what we get. X squared plus 2.2 times 10 to the power minus 2x minus 1.2 times 10 to the power minus 4 is equal to 0. So here we have the quadratic equation, and then we can solve it. How do we solve a quadratic equation? Okay, let me give you. You should know this. That is the formula for a quadratic solution. X is equal to minus b, so minus b squared minus 4ac over 2a. And the values of a, b, and c are from the coefficients in that quadratic function. And so substitute that into the values and find x. There will be two values of x here, remember, because of this plus or minus sign. One will be a positive root and the other is a negative root. Which one are you going to use? The positive root. So in our case, we are going to use the positive root, and that gives us the value of x to be okay, we calculated the values of x. What is the value of x? 4.5 times 10 to the power minus 3, and then we can now find concentration of H plus is 0.1 plus that, and it's 0.0145 and a pH of 1.84. Notice now that we have the concentration a little bit higher as we expected because of the initial concentration from 0.01, and also we see the results here is a lot more reasonable compared to what we have if we just follow through with the assumption. So be very careful when you are looking at making that assumption, especially in a case like this acid H2SO4, which is quite unique. Alright, so that brings to an end the third video of this lecture series, and thank you for listening.